Swayam Prabha. Digital India. Educated India.
Okay, so welcome students to the next class. So last time we learnt about the new concept of chemical potential, which we defined as mu, and we rewrote our first law of thermodynamics as follows. So du, then basically we added another term, so TdS minus PdV plus mu dN, right. And we saw that, so what is the role which this now chemical potential is playing in determining the heat flow in the system, right. So for example, we saw that, so in order for, so we saw that the heat, so the heat flow, or the direction of heat flow, okay. So direction of heat flow, as we already know, goes from high T, high T, high temperature to low temperature, right. So this we already knew. Similarly, we saw that the way, so the direction in which volume change happens, right, it is determined by so the pressure, so from low pressure, okay. So basically this chemical potential, this basically determined the direction of flow of particles, right. And we saw that this flow is in the direction of high mu to low mu, right. So if you have two systems in which in first system you have higher chemical potential than the other system, then the flow of particle will be from higher chemical potential to the lower chemical potential. And this is in the same way as we already know that the heat flow happens from a system which is at higher temperature to lower temperature, or the volume change happens from so the volume decreases in a system which is at lower pressure, right. So if you have two systems, one is at higher pressure and other is at lower pressure, the volume of the higher pressure system will increase and volume of the lower pressure system will decrease, right. So today what we will do is we will basically go into the third law of thermodynamics. Third law of thermodynamics. Okay, so we will see what is this third law, what are its consequences, and why it basically motivates us to come up with a new theory to understand physical systems, especially at at temperatures which are very close to zero, right. So like I said, so third law is concerned with behavior of systems in equilibrium, okay, this is important, in equilibrium as temperature approaches 0, all right. So what are the thermodynamic properties of systems as the temperature of the system is very low, right, it is almost equal to 0, all right. So let us see what happens, okay. So So, we already know, right. So, we already know that so say you have a system, right. So, consider a system where it changes its equilibrium state from one temperature to the other temperature, right. So, for a system transitioning between say a state which corresponds to a temperature Ti to a state which corresponds to temperature Tf, right. So, in this case we already know that the change in entropy will be given by the integral of dq by T integrated from Ti to Tf, right. So, this is what we know, right, and this can be written as the entropy in the final state minus entropy in the initial state, right. And initial state entropy corresponds to system at temperature Ti and final SF corresponds to system when it is at state Tf, right. So, now let us see what happens if we take Ti equal to 0, right. So, if or Tf equal to 0, all right. So, if or Ti equal to 0. So, if Ti is 0, right. So, we can write our SF minus S0. So, let us call it the entropy at temperature 0 and this will become 0 to Tf, okay. So, 0 to Tf, or I can just write T for simplification, and this is dq divided by T, right. Or I can just write the entropy of or I can even remove symbol F here. So, entropy at any temperature T is given by entropy at temperature 0 plus integral of this quantity dq by T integrated from 0 to T, right. And clearly we do not really know what is S0, right. So, this is something that we need to determine, right. So, for most of the cases we are usually only interested in entropy change, right. So, for example, if we want to know the direction in which a thermodynamic process is going, so we are mostly interested in the change in entropy, right. So, if change in entropy is positive, we know that thermodynamic process is feasible. If it is negative, we know that it is not feasible. But in some situations it actually becomes important to know exact quantity of this entropy, right. So, for example, if we want to determine the change in Gibbs potential of a certain process, right. So, for determining change in Gibbs potential and we know this is given by delta G equals minus SDT plus VDP, right, and we are not considering open systems. So, there is no mu dn like term, right. So, therefore, in this case we clearly need to know what is S, right, what is the absolute value of S, all right. So, let us see how we can determine that, right. So, what do we know about it, all right. So, now we can proceed as follows, right. So, we can write our Gibbs potential as U plus PV minus Ts, and we already know what is U plus PV, that is the enthalpy H minus Ts, right. And from this definition we know that the entropy, the value of entropy can be written as negative of partial derivative of Gibbs potential with respect to temperature at constant pressure, right. So, we can substitute this S in this equation and we can write G equals H minus T, and minus becomes plus and this becomes del G by del T at constant pressure, okay. All right. So, now what we will do is we will apply this relationship to a system which is undergoing an isobaric process from certain initial state to certain final state, right. So, apply this relationship to an isobaric process, right, which is a transition which is happening between two equilibrium states, right. So, therefore, let us say that there is a state which corresponds to symbol F like final state and initial state, right. So, therefore, I can write my GF equals HF plus T times del G by del T at constant pressure, right. And similarly, I can write the initial equation. So, G I will be H I plus T times del G by del T at constant pressure, all right. And we are also assuming that the temperature of this process is not increasing, all right, is not changing. So, therefore, I can write Gf minus Gi, equals, I am just subtracting these two equations, Hf minus Hi plus T times del by del T of Gf minus Gi at constant pressure, or I can simply write it as the change in Gibbs potential equals the change in enthalpy plus temperature times the partial derivative of change in Gibbs free energy at constant pressure, right. All right. So, this equation clearly implies, okay. So, clearly from this equation, clearly as T approaches 0, right. So, if you plug T equal to 0 in this process, we can see that delta G equals delta H, right. So, for an isobaric process, right. So, if this process is happening at constant pressure and if we take temperature to 0, then the delta G just becomes equal to delta H, all right. But experimentally it was seen, right. So, but experiments showed, right, the following, right. As T goes to 0, so in the limit T going to 0, the partial derivative of delta G with respect to temperature at constant pressure is equal to partial derivative as limit T going to 0, partial derivative of the change in enthalpy with respect to temperature at constant pressure, and both become 0, right. And if we want to visualize this, it looks something like that. So, you have temperature on x axis, and this is basically temperature 0, right, and this is the okay. So, this is delta G and this is delta H, right. So, if we calculate the slope of these lines, so they become equal to each other and equal to 0 as T approaches 0, okay. So, this is what we saw from experiments, all right. So, in particular if we look at this equation, so we can write as in the limit T going to 0, del G F by del T, right, at constant pressure minus del G I by del T again at constant pressure. So, this is equal to 0, right. And now let us see what is this del G by del T, right. So, this is nothing but the entropy. So, okay. So, which implies in the limit T going to 0, the entropy of final state minus entropy of initial state, that just becomes 0, all right. And this is one of the statements of third law, right, and this is known as Nernst's formulation of third law of thermodynamics. Okay. And this basically means that all the processes in thermal equilibrium, as temperature approaches 0, they happen without any significant change in entropy, right. So, I can maybe write here. So, all processes in thermal equilibrium happen without significant change in entropy. As temperature approaches 0. Okay. So, this is the Nernst formulation of third law of thermodynamics. Okay. So, this is the first result. But in 1911, Max Planck basically extended this hypothesis. Okay. So what he assumed, basically, so Planck extended the Nernst's hypothesis by assuming. Okay, so the assumption that he made was as follows. So as limit t goes to 0, the variation of Gibbs potential becomes equal to the variation of enthalpy, and this is, so this is the assumption that he made. So this is the first assumption, right, and the other assumption was limit, in the limit t going to 0, the partial derivative of Gibbs potential with respect to temperature at constant pressure also becomes equal to the partial derivative of enthalpy with respect to temperature at constant pressure, right. Okay. So these are the two assumptions that he made, and you can actually see it here, right. So G equals H plus T times del G by del T, right. So if you put T equal to 0 in this case, so you can see that the Gibbs potential and thermodynamic and enthalpy, they become equal to each other, right. And another assumption that he made was that not only G and H become equal, but as T approaches 0, so the partial derivative of Gibbs potential with respect to temperature also becomes equal to partial derivative of enthalpy with respect to temperature at constant pressure. Okay. So now let us see, by under these assumptions, what is the result that we get, right. So let us for convenience, let us define a quantity phi which is equal to G minus H, all right. And we already know, so since G equals H plus T times del G by del T at constant pressure, right. So if I take H to the other side, I can write phi equals T times del G by del T at constant pressure, and let me call this equation number 3, right. So clearly, okay, so now from equation 1 and 2, so from 1 and 2, so if I take this to the other side, I can write, so in the limit t going to 0, so G minus H, like I have defined, the phi becomes 0. Also if I now take this on the other side, so in the limit t going to 0, so del, so G minus H is phi, so del phi by del T at constant pressure is also 0. Okay. Okay. So what now we will do is, so we will add minus T times del H by del T at constant pressure to both sides of equation 3. Okay. So let us just add this quantity to both sides on equation 3 in equation 3, all right. So we can see that so we end up with phi minus T times del H by del T, and this becomes equal to T times del G by del T at constant pressure minus T times del H by del T at constant pressure, right. So this I can this I can rewrite as follows. So if I move this on the if I move this on the other side, right, so this becomes so this becomes G minus H, right. So this becomes T times del phi by del T at constant pressure minus phi equals minus T times del H by del T at constant pressure. Okay, so having done that, so clearly we can, so now we can divide by T on both sides. So we can rewrite this as follows. So del phi by del T at constant pressure minus phi divided by T equals minus T times del H by del T at constant pressure, right. So now, now like we just saw, in the limit T going to 0, phi goes to 0, right, and we have a quantity which is phi by T, right. So since limit T going to 0, phi is also 0, this implies in the limit T going to 0, this quantity phi by T can just be written as, can be simply written as in the limit T going to 0 del phi by del T at constant pressure, and this is basically, if you know, it is known as L'Hopital's rule. L'Hopital rule. Okay. Okay, so we can just rewrite this as follows. So therefore, if I just substitute this here, so what we if I so the left hand side LHS becomes 0, and this simply implies that in the limit T going to 0, the right hand side, which is del H by del T at constant pressure, is also 0, right. Right. And since under this assumption number 2, right, so this del H by del T I can just rewrite as follows. So in the limit T going to 0, so this just becomes del G by del T at constant pressure, this is 0, and what is del G by del T as T goes to 0? This is nothing but the entropy. So entropy of any system as temperature goes to 0 becomes 0. Okay. So this result tells us that as the temperature approaches 0, the entropy goes to 0, all right, and this is known as, okay, so I can write this again. So in the limit T going to 0, S of T is equal to 0, right, and this is known as Planck's statement of third law. Okay. So this is the third, this is another statement of the third law, right, and in words I can write, so the entropy of an equilibrium system at T equal to 0 is also 0, is 0. Okay. So this is another important outcome of this of this third law, all right, and this has been actually shown that for crystalline solids this indeed is true, right. So because there is just one way in which you can arrange all your atoms, right, in a lattice, in a proper lattice positions. However, there are certain cases like glasses where this is not true, right. So therefore we can always find some exceptions where this law breaks down, but then you can also say that glassy systems are not really equilibrium systems, right. So this statement only is valid for systems which are truly achieved equilibrium, and at T equal to 0 the entropy has to be 0, all right. So having said that, now what we will do is we will look at the consequences of this third law. Okay. So basically we have now seen two statements of third law. So one statement is that which is due to Nernst, right. So he says that as temperature approaches 0, so all the thermodynamic processes in equilibrium, they happen without any change in entropy, right. So change in entropy is 0 when temperature is 0. And Planck extended that result by basically showing that the entropy of any equilibrium system becomes 0 at absolute 0. Okay. So let us see what are the consequences of third law. Okay. So the first consequence is that, okay, so for all solids, right, the expansivity coefficient, maybe I can, expansivity coefficient becomes 0 as t goes to 0. Okay, so let us see how we can see that, right. So remember how we define especially isobaric expansivity, right. So isobaric which we denoted by a symbol beta p. Okay, so this is the fractional change in volume of a material with respect to temperature at constant pressure, right. But we know from Maxwell's relation, so from Maxwell's relation, okay, from Maxwell's relation, so del V by del T at constant pressure is equal to negative of del S by del P at constant temperature, right. Okay, but we know that from okay, but we also know, okay, but from Nernst's third statement, right, what is this quantity, right. So in the limit T going to 0, so this change in entropy as a function of pressure, right, as a function of pressure basically becomes 0, right, because the Nernst statement is basically telling you that as temperature approaches 0, there is no change in entropy, right. So the numerator will become 0. So therefore, so this implies del V by del T at constant pressure is also 0, and if we plug this here, and this naturally implies that the expansivity of solids, I am saying solids because we are at very low temperatures, the only phase which is possible is solids, right. So solids do not really expand upon heating, right. So this means solids do not expand upon heating as T goes to 0. Okay, so this is one of the consequences of third law. Okay, so let us talk about the second one. So basically the slope of phase transition curves. Okay, so two classes before we talked a lot about phase diagrams and phase transitions, and a typical phase diagram which I always plotted that looked something like this, right. So you had so you had a solid phase, this is temperature, this is pressure. So at very low temperatures you had a solid phase, in between you had a liquid phase, and we had a gas phase, right. And of course there was a triple point and a critical point and so on. Okay, so let us see how okay, so and of course we also saw that how we can mathematically calculate the shape of these curves, right. So now let us see how these phase boundaries, these solid lines, they get influenced as we approach temperatures which are close to 0. Okay, so during phase transition, so we saw an expression, right, we derived an expression which looked like this. So dP by dt, the change of pressure with respect to temperature was given by S2 minus S1 divided by V2 minus V1, right, where S2 was the specific entropy in phase 2, S1 was the specific entropy in phase 1. Similarly, V2 was the specific volume in phase 2 and V1 was the specific volume in phase 1, all right. But again, since we know that as temperatures go to 0 from the statement of third law by Nernst, S2 minus S1, since the processes close to T equal to 0 happen without any change in entropy. So this is also 0. This naturally implies that the slope of P versus T curve also becomes 0, right. And basically what it says is, so as temperatures approach absolute 0, okay, so maybe I can draw this, redraw this, okay. So especially the phase boundary, between solid and gas, okay, as temperatures approach 0, the slope vanishes, right. The slope of this line as T equal to 0, that vanishes, all right. So that is another result, that is an outcome of the third law of thermodynamics, right. And there are some very careful experiments that have been done with solid helium, right, which have shown. So okay, so experiments on solid helium close to T equal to 0, right. So they have indeed seen that the way so dP by dt, right. So the phase, from the phase diagram, they have seen this curve behaves as a 7th power of temperature, right. And you can see if temperature goes to very small value, this value goes to 0 really quickly, right. So therefore this kind of validates the result that that is a consequence of third law of thermodynamics, okay. So basically what I am saying, so this approaches 0 very fast, right, since there is a 7th power as T goes to 0, okay. So this is another consequence of third law of thermodynamics, okay. So what happens to heat capacities, right. So the third consequence is, so heat capacities at T approaching 0, okay. So as T approaches 0, okay. So let us write the definitions of heat capacities. So we know that heat capacity at constant volume can be written as T times del S by del T, at constant volume, and Cp equals T times del S by del T at constant pressure, right. Also we can write the change in entropy. So S minus S0, say we are going from temperature state 0 to some finite temperature. So the change in entropy just simply becomes 0 to T Cv dt by T, right. And or I can be little bit more. Okay, so I can write Cv as a function of, so this is like varying as a function of temperature by T, and say if your process is happening at constant pressure, so S minus S0 becomes integral 0 to T of Cp, which is a function of temperature, divided by T, right. So now clearly, right, so clearly we can see, okay, okay, so as T goes to 0, right, so in the limit of temperature going to 0, we know that S0 is 0, right. This is the Planck's statement of third law, that the result that we obtained for the third law, and since as T goes to 0, so and T sits in the denominator on the right hand side, right, and we know that left hand side is finite, right. So at any finite temperature the entropy is positive. So in order for this to get a finite positive outcome from this equation, right, this equation, we must have the condition that the Cp and Cv, that should also go to 0 in the limit T going to 0, right, and this should happen, okay. So this should happen in okay. So so what I am saying is, as T goes to 0, the specific heats should also approach 0, and they should approach at least at the rate given at the rate of the order of T, right. So C, either P or V, should go as so it is a function of temperature, and it should decay to 0 with a power which has to be greater than or equal to 1, right. So the dependence of this specific the heat capacity with temperature has to have a relationship which is which has a temperature with temperature with a power which is at least 1 or greater than 1, all right. And there are ample experimental evidences which actually confirm this. So, heat capacities indeed they go to 0 as we approach very low temperatures, right, and this is experimentally verified. Okay. So, this result indeed is experimentally verified that heat capacities they do approach 0 as temperature goes to 0, all right. And another consequence of third law is what happens to the Carnot's efficiency. Okay. So, we know the way we defined, so the Carnot efficiency was given by 1 minus TL by TH, right. So essentially an engine which is operating between two temperatures, two reservoirs kept at a low temperature of TL and a higher temperature of TH, the efficiency is given by 1 minus TL by TH, right. But now we can see if we operate this engine between a reservoir, a cold reservoir which is set at a temperature equal to 0, right. So, if TL is set at 0, this implies our eta is equal to 1, right. And what does that mean, right. So, that means complete conversion of heat to work is possible, right. And this statement essentially is against the second law of thermodynamics, right. So, second law of thermodynamics explicitly told that the heat cannot really flow from so you can't really extract work from a system with 100% efficiency, right. So, efficiency has to be less than 1, okay. And so this also in some sense imply that achieving T equal to 0 state is impossible, right. So, this means that in order for second law of thermodynamics to be valid, we must have so T equal to 0 state must not be possible to achieve, right. So, if we can achieve a system which is at T equal to 0, we can run a Carnot engine between a hot reservoir and a cold reservoir kept at 0, and we can go against the second law of thermodynamics, right. So, therefore, the another natural consequence of this third law is that it is impossible to achieve a state which is exactly at temperature equal to 0, right. So, basically unattainability of T equal to 0 state. Okay. So, what do we mean by that? Okay. So, it turns out this is basically another statement of third law, and it means it is impossible to cool a system to T equal to 0 in finite number of steps. Okay. So, it is impossible to achieve that state, right. So, how do we conceptualize that? Okay. So, again we will write down that expression. So, entropy of the system at any temperature is equal to so the integral of okay. So, say entropy of that system at T equal to 0 plus integral 0 to T of C dt by T, right, and where C is the heat capacity, either Cp or Cv, right. So, depending upon whether we are doing this process at a constant pressure or constant volume. Okay. So, say now we have some external parameter, external knob with which we can make two distinct equilibrium states, right. So, equilibrium state 1 and equilibrium state 2, all right. So, okay. So, say using So, using an external parameter, we make two equilibrium states, right. Okay. And for state 1, its dependence of entropy with temperature can be written as S1 T equals S1 T equal to 0, which I am just writing at 0, plus 0 to T of C1 dt by T, right. So, the C1 is the heat capacity of the system 1, and similarly I can write S2 of T equals S1 of 0 plus 0 to T of C2 dt by T. Okay. Okay, so let us call this equation 1 and call this equation 2, right. So, subtracting 1 from 2, okay, so we get S2 of T minus S1 of T equals S2 of 0 minus S1 of 0 plus integral 0 to T C2 dt minus C1 dt by T. All right. Okay. But what we can okay, so actually we can plot this dependence of entropy as a function of temperature as follows, right. So, what this is telling us is that the entropy of the system increases with temperature through this relationship, right. So, say this is a T equal to 0, right. So, this is T equal to 0. So, for system 2, okay, so for system 2 the entropy is increasing like this, right, and similarly there is certain increase. Okay, so this is the general increase in this is how the entropy increases with temperature, and this functional form will depend upon the specific system that we are studying, right. Okay, so let us look at this equation again, right. So, there is a term on the right hand side which is as follows. So, this is S2 0 minus S1 0, right. So, let us see if this if the difference of S2 0 and S1 0 is non-zero, right. So, which means we have a situation where the entropy of the state 2 is increasing like this, and this is T0 and this quantity will be S2 of 0, right, and the entropy of the other state is also varying something like that, all right. So, this is S1 T and this is S1 equal S1 0, right. And now we can see that in order to achieve T equal to 0 state, I can do series of processes, series of isothermal and adiabatic processes to achieve T equal to 0 state, right. So, say I undergo an isothermal process which I am denoting by a red line, and then I undergo an adiabatic process, right, where the entropy change is 0, then I undergo another isothermal process, another adiabatic process, right, and so on. Okay. And if I continue to do that, I will achieve a state which is T equal to 0, right. So, from this graphical representation we can see, so if S2 minus S1 at T equal to 0 is non-zero, it is possible to achieve T equal to 0 state with finite number of isothermal and adiabatic processes, right. And here the red line is isothermal process, and the blue line is adiabatic process. Okay. So if this is if S2 minus S1 is indeed non-zero, then we should be able to achieve T equal to 0 state within certain finite number of these isothermal adiabatic processes. But we know that according to but from Nernst statement, right. So from Nernst statement, right. So we know that S2 0 minus S1 0 is 0, right. And in fact, we also know that S2 0 minus S2 0 equals S1 0, and this is also equal to 0, right. So this is the Planck's statement. Okay. So how does this curve changes, right. So this is when S2 minus S1 is non-zero. But what happens to this plot if S2 and S1 are all 0? Okay. So in this case, I can again draw, this is S2 of t, this is S1 of t, right. And now let us see what happens if I again do a series of isothermal and adiabatic processes, right. So if I do my first isothermal, okay, so again, so this is temperature, this is entropy. Okay. So there is my first isothermal process, then I do another adiabatic process. If I do another isothermal process, another adiabatic, okay. And you can see that since these curves are converging with each other as, okay, so as S goes to 0 and T goes to 0, okay. So this is S equal to 0 and T equal to 0, right. So this point is S 0 and T 0, and since these curves are getting closer and closer to each other, their slopes are matching, and they are basically going to the same, they are intersecting, right. So it will take me infinite number of processes to actually go to T equal to 0 state, right. So you can see that I am basically squishing and packing more and more number of these processes between this small region, right. So therefore in theory it will take me infinite number of processes to actually achieve the state which is T equal to 0, right. So this basically implies if, okay, so if this is true, right, so this basically implies that curves intersect at T equal to 0, and this implies that we need infinite number of isothermal adiabatic processes to attain or to achieve T equal to 0 state, right. Or in other words, in finite number of processes, it is impossible to achieve T equal to 0 state, all right. So therefore that proves that no matter what we do, it is impossible to attain T equal to 0 state, all right. So it is impossible to create a system which is at absolute 0 temperature, and this is actually not a bad thing, because if we could do that, then that will go against the second law of thermodynamics, because we know from the Carnot engine, Carnot efficiency, the efficiency of such an engine which is operating between certain finite temperature and 0 temperature, it will go to 1, all right. But again, you probably must have realized, so this puts us into very difficult situations, right. So as we take our systems to very low temperatures, we start contradicting ourselves, right. So for example, how do I make sense of operating an engine which is operating between a reservoir which is kept at 0, right. So how can a reservoir undergo an isothermal process at T equal to 0, right. So if you remember, in a Carnot cycle, Carnot engine, we dump heat into the system, right, and if we dump heat into a reservoir at T equal to 0, it will warm up, right, its temperature will, is bound to change, right. So therefore it is actually, so it is actually very difficult to capture the properties of systems which are very close to T equal to 0 using the principles of thermodynamics, right, and therefore it is even said that so it is even said that, so third law is a separate postulate on its own, right, and it is independent of the second law, all right. So therefore there is a need to create a new theoretical formulation to especially to understand systems which are at very low temperatures, and that is where we will basically end the part of thermodynamics, and we will slowly transition into statistical physics, right, and we will see how that formulation is better than thermodynamics, right. So that we will do in the next class. Okay. So thank you very much.